Imagine holding a piece of history in your hands, something crafted over 1,000 years ago, yet so advanced that it defies everything we thought we knew about ancient technology. This isn't just any artifact, it's a chalice that shifts from emerald green to blood red as light passes through it, as if it holds a secret whispering across centuries. This is the Lycurgus Cup, a Roman masterpiece that shouldn't exist. How could artisans from the 4th century create something that changes color like magic? The answer lies in a discovery so cutting-edge, it wouldn't be understood until the modern era, nanotechnology. Picture this: a world where emperors ruled, gladiators fought, and glassmakers, armed with nothing more than fire and ingenuity, stumbled upon a technique so precise it manipulates particles invisible to the naked eye. The Lycurgus Cup isn't just beautiful, it's a scientific marvel. When light hits its glass, tiny flecks of gold and silver, smaller than a grain of sand, scatter the light in a way that transforms its hue. This isn't a trick of the light or a quirk of chemistry. It's deliberate. It's engineering on a scale so minute it borders on the impossible. And yet, here it is, a relic that predates microscopes, labs, or even the concept of atoms. What makes this cup even more extraordinary is that it's not alone. Across history, there are whispers of other objects that seem to bend the rules of their time, artifacts that challenge our understanding of human innovation. But the Lycurgus Cup stands apart. It's a puzzle wrapped in glass, a testament to how much the ancients knew and how much we've yet to uncover. As we peel back the layers of this mystery, we'll explore how modern science cracked its code, what it reveals about the ingenuity of the past, and why this tiny cup might just rewrite a chapter of history. This isn't just a story about glass. It's about the timeless human drive to create, to experiment, and to leave behind wonders that leave future generations in awe. The Lycurgus Cup first resurfaced in the 19th century, emerging from the shadows of history like a relic from a forgotten dream. Its exact origins remain hazy. No grand excavation or dramatic uncovering marked its return. Instead, it slipped quietly into the hands of collectors, a curious oddity among ancient treasures. By the time it found its permanent home in the British Museum, scholars were already scratching their heads. Here was a glass vessel, delicate yet defiantly intact, shimmering with an otherworldly color shift that defied logic. When lit from behind, the opaque green glass would ignite into a fiery red, as if the cup itself held a living ember. At first, historians assumed it was some trick of the light or a quirk of aging glass, but the more they studied it, the more baffling it became. This wasn't a mere chemical reaction or a patina formed over centuries. The cup's behavior was too precise, too intentional. It wasn't until much later, with the advent of powerful microscopes, that scientists uncovered the truth. The glass was embedded with particles of gold and silver so minuscule they were invisible to the naked eye. These weren't accidental impurities, they were engineered, meticulously ground down to sizes smaller than a wavelength of light. Today, the cup sits in London, a silent witness to a technological leap that shouldn't have been possible for its time. Visit the British Museum and you'll see crowds gathering around its display, drawn by rumors of its strange properties. Some lean in, waiting for the light to shift, hoping to catch that fleeting moment when green bleeds into red. Others study the intricate carvings of King Lycurgus entangled in vines, a myth frozen in glass. But the real story isn't just in the artistry, it's in the science hidden within. A secret the Romans mastered centuries before the word nanotechnology even existed. What else might they have known? The cup doesn't give up its secrets easily. It's a riddle wrapped in craftsmanship, waiting for the next curious mind to unravel it. Standing just 16.5 centimeters tall, about the height of a modern coffee mug, the Lycurgus Cup is deceptively small for the colossal secrets it holds. Crafted in 4th century Rome, this isn't just a drinking vessel, it's a storytelling masterpiece. The glass swirls with a scene ripped straight from myth, King Lycurgus of Thrace, his body twisted in perpetual struggle, ensnared by vengeful vines. According to legend, Lycurgus angered the god Dionysus by banning his wild celebrations, and the cup freezes that moment of divine punishment in stunning detail. The king's face contorts in fury and desperation as the tendrils tighten around him, their leaves and stems rendered with such precision you can almost see them quiver. What's astonishing isn't just the artistry but the medium itself. The cup is made from dichroic glass, a material so rare in antiquity that only a handful of examples survive. In ordinary light, the glass glows a deep, mossy green, the figures emerging like shadows in a forest, but tilt it toward a light source and the entire scene transforms. The green melts into a luminous ruby red, as if the cup is filled not with wine but with liquid fire. This isn't a trick of the light. It's the work of artisans who understood their materials on a level that still stuns scientists today. Every inch of the cup whispers of its origins. The glass is thick yet astonishingly clear, free of bubbles or distortions, a testament to Roman glassmaking at its peak. The figures are carved with a jeweler's precision, their depth creating shadows that shift as the cup turns. And then there's the rim, delicately flared, as if inviting the drinker to partake in both the wine and the myth itself. But the true marvel lies in what you can't see. Those minuscule flecks of gold and silver, ground finer than pollen, suspended in the glass like stars in a twilight sky. To the naked eye, they're invisible, yet without them, the cup's magic, its very soul, wouldn't exist. This isn't just a relic, it's a conversation across time. When you peer into its depths, you're not just seeing a king trapped in vines. You're witnessing the moment art collided with science, where craftsmen, armed with nothing more than kilns, rudimentary tools, and an almost alchemical understanding of their materials, achieved the impossible. The Lycurgus Cup doesn't just tell a story, it is one, and every curve, every hue shift is another line in a manuscript we're still learning to read. Hold the Lycurgus Cup under sunlight and it glows like jade, a deep, opaque green that seems to swallow the light. But tilt it just so, let the light pass through instead of bouncing off, and something extraordinary happens. The green dissolves, replaced by a swirling, translucent red so vivid it looks like the glass is stained with pomegranate juice. This isn't a trick of the light or an illusion of aging. It's a deliberate, calculated effect, one that no other surviving piece of ancient glass comes close to replicating. The secret lies in what scientists call dichroism, a property where a material appears to change color depending on how light interacts with it. Modern technology uses this principle in everything from sunglasses to spacecraft windows, but the Romans cracked it over a millennium before the word dichroism even existed. When researchers finally examined the cup's glass under electron microscopes in the 20th century, they found it peppered with gold and silver particles so tiny, they're measured in nanometers, smaller than a single bacterium. These particles don't just sit there, they dance with light. Here's how it works. When light hits the cup from the front, those flecks of gold about 50 nanometers wide reflect the green wavelengths, giving the glass its emerald hue. But when light shines through the glass, the silver particles, even smaller at around 100 nanometers, absorb the blue and green light, letting only the red pass. The result, a color shift so dramatic it feels like holding two different cups in one. To the naked eye, it's pure alchemy. In reality, it's a breathtaking feat of precision engineering. What's even more mind-bending is that these artisans weren't working with microscopes or precision scales. They couldn't see the particles they were manipulating. Yet somehow, through trial and error or perhaps a closely guarded technique, they discovered that grinding gold and silver to dust and mixing them into molten glass in exact proportions would create this mesmerizing effect. Imagine the patience it took. Too much gold and the cup would lose its transparency, too little silver and the red would never ignite. This wasn't just decorative flair. The color shift carries symbolic weight. In reflected light, Lycurgus is trapped in his vine prison, the green evoking nature's dominance, but when backlit, the red spills forth like wine or blood, hinting at Dionysus's wrath. The cup doesn't just depict a myth, it performs it, pulling the viewer into the story with every tilt. No other artifact from antiquity achieves this. Byzantine mosaics glitter with gold, Egyptian glass shimmers with cobalt, but nothing changes like the Lycurgus Cup. Even today, replicating its properties requires nanotech expertise. So how did the Romans stumble upon this? Was it luck, or did they know more about light and matter than we've given them credit for? The cup refuses to answer, leaving us to marvel at the line between ancient craftsmanship and what we'd call modern science. For decades after its rediscovery, the Lycurgus Cup was a riddle wrapped in glass. Scholars grappled with its color-changing trick, tossing theories back and forth like dice in a Roman tavern. The earliest explanations leaned on the familiar. Perhaps the glass was stained with organic dyes that degraded unevenly over time, creating a patchwork of hues. Others suggested metallic impurities, copper or iron, had seeped into the material, reacting with centuries of burial conditions to produce the shift. These were comforting ideas rooted in what was known about ancient crafts. But the cup refused to comply. Testing these theories only deepened the mystery. Dyes would have faded or blurred, but the cup's color transition remained razor-sharp. Impurities couldn't explain why the effect was so consistent, so controlled. If it were accidental, why didn't other Roman glass, even pieces buried alongside it, display the same behavior? The scientific community hit a wall. Here was an artifact that clearly followed rules, just not any they recognized. Frustration grew, punctuated by moments of near discovery. In the 1960s, one researcher proposed the color came from tiny metal particles, but without the tools to see them, the idea was dismissed as speculative. The breakthrough came from an unexpected place: mid-century aerospace research. Scientists studying how light interacts with metals at microscopic scales realized certain particle sizes could scatter specific wavelengths, precisely what the cup was doing. When electron microscopy finally revealed gold and silver nanoparticles in the glass, it wasn't just a eureka moment, it was a humbling one. Generations of experts had been staring at the answer without the means to perceive it. The Romans hadn't stumbled upon a happy accident. They'd perfected a recipe, one that demanded exact proportions, meticulous grinding, and a craftsman's intuition for how materials behaved beyond the limits of human vision. What's striking isn't just that earlier theories were wrong, but why they failed. They assumed the ancients worked with the same toolkit scholars had in the lab: visible ingredients, measurable reactions. No one considered that Roman artisans might have mastered phenomena invisible to the naked eye. The cup didn't just defy expectations, it exposed the blind spots in how we view history. We expect technological progress to move in a straight line, but the Lycurgus Cup whispers a different truth. Sometimes knowledge is lost, buried, waiting to be rediscovered by minds ready to see the unseen. The truth about the Lycurgus Cup was hidden in plain sight for centuries, locked inside its glass like a whispered secret. It wasn't until the mid-20th century, when scientists finally wielded a tool powerful enough to peer into the infinitesimal, that the mystery unraveled. Electron microscopes, machines capable of magnifying objects millions of times, revealed what no Roman artisan could have seen: a constellation of gold and silver particles, each one smaller than a wavelength of light, suspended like celestial dust in the glass. These weren't just random flecks, their size was precise, uniform, and deliberate. The gold particles measured around 50 nanometers across, so tiny 10,000 could fit on the head of a pin. The silver particles were slightly larger, yet still invisible without magnification. Under the microscope, their arrangement looked less like an accident and more like a carefully orchestrated dance. When light struck them, the gold scattered green wavelengths, while the silver absorbed blues and greens, allowing only red to pass through. This wasn't alchemy, it was physics harnessed with astonishing precision. What's remarkable isn't just the discovery itself, but how it rewrote history. Before this, scholars assumed nanotechnology was a modern breakthrough, born from labs with billion-dollar equipment. Yet here was proof that ancient craftsmen had manipulated matter at the same scale, achieving effects that wouldn't be replicated until the space age. The Romans didn't have the language of nanoparticles or quantum mechanics, but they'd stumbled upon their principles through sheer experimentation. They knew that grinding gold and silver to incomprehensibly fine dust and mixing them into molten glass in exact ratios would create this magic. The implications are staggering. If they could control particles this small, what else did they understand about materials that we've since forgotten? The cup hints at a lineage of lost knowledge passed down through guilds or workshops erased by time. It's a reminder that technological progress isn't always linear. Sometimes it loops back, burying brilliance until new tools dig it up again. Today, the Lycurgus Cup sits at the crossroads of art and science, a testament to human curiosity. Those nanoparticles, invisible for 16 centuries, now speak volumes. They tell us that genius isn't bound by era, that innovation, even when forgotten, leaves echoes, and sometimes all it takes is the right lens to hear them. Now let's take a closer look at what makes the Lycurgus Cup's glass so extraordinary. The gold and silver nanoparticles themselves. These aren't just specks of metal randomly mixed in. They're meticulously sized between 40 and 70 nanometers, with gold making up roughly 66% of the blend and silver accounting for the remaining 34%. To put that into perspective, a single strand of human hair is about 80,000 nanometers thick. The particles in this cup are thousands of times smaller, invisible not just to the naked eye but to any tool the Romans could have possessed. What's astonishing isn't just their size but their consistency. Modern analysis shows these particles weren't haphazardly scattered. They were evenly distributed throughout the glass, a feat that suggests an almost obsessive level of control. The gold, at around 50 nanometers, was fine-tuned to interact with green light, while the slightly larger silver particles absorbed blue and green wavelengths, allowing red to dominate when light passed through. This precise ratio, 2 parts gold to 1 part silver, wasn't arbitrary. It was the sweet spot, the perfect balance to create that mesmerizing color shift. How did Roman artisans achieve this without microscopes or precise measuring tools? The answer likely lies in a combination of intuition, generations of trial and error, and a deep, almost instinctual understanding of their materials. They may have started by grinding gold and silver into the finest powder possible, then melting them into the glass at specific temperatures. Too much heat, and the particles might clump together, ruining the effect. Too little, and they wouldn't disperse evenly. The process would have been as much art as science, relying on subtle changes in color or viscosity to gauge success. Even more intriguing is the possibility that this wasn't a one-off experiment. The uniformity of the particles suggests a standardized method, perhaps passed down through workshops or guilds. Other Roman glass fragments with similar properties have been found, though none as stunning or well-preserved as the Lycurgus Cup. This hints at a broader tradition, a lost school of craftsmanship that understood light and materials in ways we're only now rediscovering. Today, scientists use advanced spectroscopy and electron microscopes to replicate this effect, but the Romans did it with fire, patience, and an uncanny eye for detail. Their nanoparticles weren't just tiny, they were engineered, each one a tiny architect of light. And that's what makes this cup not just a relic, but a bridge between ancient ingenuity and modern science. The next time you hear someone call nanotechnology a product of the 21st century, remember, the Romans were working on it 1700 years ago. Roman glassmakers were master alchemists, turning sand and fire into objects of breathtaking beauty and technical brilliance. By the time the Lycurgus Cup was crafted in the 4th century, Roman glassblowing had already reached astonishing heights. Think of the famed Barberini Cup, another dichroic masterpiece that shimmers between amber and blue depending on the light. But while the Barberini Cup is stunning, it relies on comparatively crude methods. Streaks of colored glass layered like ribbons, their hues shifting as light catches different angles. The Lycurgus Cup, by contrast, isn't just layered, it's alive with nanoparticles, a leap forward so advanced. It's as if the Romans skipped ahead 1,500 years in material science. To understand the gap between these two cups, picture the difference between painting with broad strokes and etching at the atomic level. The Barberini Cup's dichroism comes from macroscopic bands of glass, each tinted with metal oxides like cobalt or manganese. When light hits these bands, some colors are absorbed while others bounce back, creating a two-tone effect. It's beautiful, but it's a blunt instrument compared to the Lycurgus Cup's precision. Where the Barberini relies on millimeters-thick layers, the Lycurgus manipulates particles 1,000 times smaller, engineering light itself at the scale of individual photons. The Romans didn't stumble upon this nanotechnology by accident. Glassmaking in antiquity was a fiercely guarded trade, with workshops passing down techniques like sacred texts. Craftsmen knew that adding metals to molten glass could alter its color: gold for ruby red, silver for sunny yellows, but the Lycurgus Cup's creators went further. They didn't just dissolve metals into the glass, they ground them into dust so fine it behaved unlike anything else in nature. Imagine the trial and error this required, grinding gold with mortar and pestle for hours, testing batch after batch, refining the process until the particles were small enough to scatter light predictably. This wasn't decoration, it was proto-science, a dance of chemistry and physics conducted in kilns rather than labs. What's even more remarkable is how few examples survive. Only a handful of Roman glass fragments show similar nanoparticle effects, suggesting the Lycurgus Cup might represent the pinnacle of a lost art. Perhaps the technique was too labor-intensive, or the knowledge too closely held by a single workshop, vanishing when Rome fell. Whatever the reason, the cup stands alone, a relic of what could have been an entire tradition of nano-engineered art. Today, we'd use centrifuges and chemical reactions to achieve similar effects. The Romans did it with fire, patience, and an artisan's intuition. That's the real wonder here, not just what they made, but how they thought. They didn't have the word nanoparticle, but they understood its power. And in that understanding, they left us a chalice that still defies expectations, glowing green and red across the centuries like a beacon from the past. Nanotechnology sounds like the stuff of futuristic labs, a field where scientists in sterile suits manipulate atoms to build supermaterials or microscopic machines. By definition, it's the science of controlling matter at the scale of 1 to 100 nanometers. To grasp just how small that is, picture slicing a single human hair lengthwise 1,000 times. Each of those slivers would still be thicker than the nanoparticles in the Lycurgus Cup. Today, we use this technology to create everything from ultra-efficient solar panels to targeted cancer treatments. But here's the twist: Romans were doing it 17 centuries ago. The gold and silver particles suspended in the cup's glass aren't just small, they're precisely small. Ranging between 40 and 70 nanometers, they occupy a sweet spot where physics gets weird. At this scale, metals don't behave like bulk materials. Instead of reflecting light predictably, they interact with specific wavelengths, absorbing some and scattering others. This phenomenon, called surface plasmon resonance, is why the cup shifts from green to red. Modern scientists harness this same principle in medical diagnostics and even stained glass for churches. But the Romans, they cracked it without knowing atoms existed. Think about what that means. These artisans couldn't see what they were working with. They had no concept of nanometers, no electron microscopes to confirm particle size. Yet through sheer experimentation, grinding, melting, Observing, they stumbled upon a process that modern labs struggle to replicate without billion-dollar equipment. It's as if a medieval blacksmith accidentally forged a microchip. Even more astonishing, the ratio of gold to silver in the glass is consistent across the entire cup. This wasn't a lucky one-off, it was a repeatable technique honed through generations of trial and error. What's equally mind-bending is how this reshapes our view of ancient innovation. We often frame technological progress as a straight line, with each era building on the last. But the Lycurgus Cup is a reminder that knowledge isn't always cumulative, sometimes it's cyclical. The Romans achieved nanoscale precision, then the recipe vanished for over a millennium. When 20th century scientists rediscovered these principles, they branded them as breakthroughs. In truth, they were echoes. Today, we use nanoparticles to purify water, deliver drugs, and even build flexible electronics. The irony: many of these applications rely on the same light-scattering properties the Romans mastered. Their cup wasn't just art, it was a prototype, a pocket of proto-science hidden in plain sight. So the next time someone calls nanotechnology a modern miracle, remember, the real miracle is that we ever forgot it. Was the Lycurgus Cup's nanotechnology intentional or just a stroke of luck? The answer lies somewhere between meticulous craftsmanship and the kind of happy accident that changes history. On one hand, the evidence screams deliberation. The particles aren't randomly scattered. They're uniform, sized between 40 and 70 nanometers with a consistent gold-to-silver ratio. That level of precision doesn't happen by chance. Roman glassmakers didn't have electron microscopes, but they had something just as powerful: generations of hands-on experimentation. They knew that grinding gold and silver to dust and melting them at specific temperatures could alter glass in magical ways, even if they didn't understand the physics behind it. Consider the furnace conditions. Roman kilns could reach temperatures hot enough to liquefy glass, but controlled enough to prevent nanoparticles from clumping. Artisans would have relied on subtle cues, the way molten glass shimmered or how long metals took to dissolve, to gauge success. This wasn't guesswork, it was a refined craft honed through trial and error. And let's not forget the cup's design. The color shift isn't just decorative, it mirrors the myth of Lycurgus: green for the vines trapping the king, red for Dionysus's wrath. That symbolism feels too deliberate to dismiss as coincidence, yet there's a compelling counter-argument. No other Roman artifact achieves this effect so flawlessly. If nanoparticle engineering was a known technique, why aren't there more examples? Perhaps the Lycurgus Cup was a serendipitous outlier, a batch where gold and silver happened to grind finer than usual, or where furnace conditions aligned just right. After all, ancient workshops were full of unpredictable variables: impure metals, inconsistent heat, human error. Maybe the cup's creators were as stunned by the result as we are. But here's the clincher: other fragments of Roman glass do contain traces of similar nanoparticles, though none as striking. This suggests the Lycurgus Cup wasn't alone. It was the pinnacle of a rare, elite practice. The knowledge might have been confined to a handful of master artisans, lost when Rome's glassmaking hubs declined. So was it purposeful, likely accidental? Not entirely. The truth probably blends both: a culture of relentless experimentation, stumbling onto brilliance, then refining it into something sublime. The real question isn't whether the Romans understood nanotechnology, it's whether they needed to. They didn't have the vocabulary, but their hands knew the way. And in that space between intuition and science, they left us a relic that still dazzles, a reminder that genius doesn't always wear a lab coat. Sometimes it wears the soot-stained hands of a glassblower, pulling miracles from fire and patience. To understand the magic of the Lycurgus Cup, we need to peer into the invisible world where light and matter collide. At the heart of its color shift lies a phenomenon called surface plasmon resonance, a term that sounds complex but boils down to a simple principle. When light hits metal particles smaller than its wavelength, strange things happen. Imagine tossing a pebble into a still pond. The ripples spread outward in perfect circles. Now picture that same pebble dropped into a teacup. The ripples crash into the sides, folding back on themselves in chaotic patterns. That's essentially what's happening inside the cup's glass, but with light waves instead of water. The gold and silver nanoparticles act like microscopic trampolines for light. When white light, a mix of all colors, strikes them, the particles' tiny size means they can't absorb all that energy evenly. Instead, they selectively scatter specific wavelengths based on their own dimensions. Gold particles around 50 nanometers wide are perfectly tuned to bounce back green light, giving the cup its jade-like glow in reflected light. Meanwhile, the slightly larger silver particles absorb blues and greens, acting like a filter that only lets red wavelengths pass through when light shines from behind. This isn't just color, it's physics playing out at a scale so small it defies intuition. What's fascinating is how precisely these particles had to be crafted. A few nanometers larger or smaller, and the effect would vanish. The spacing between particles matters too. If they're too close, they clump and lose their magic. Too far apart, and the light doesn't interact strongly enough. The Romans somehow found the Goldilocks zone for both size and distribution without any way to see what they were doing. It's like tuning a radio to a perfect frequency by ear, blindfolded. Modern scientists use this same principle in everything from medical tests to solar panels. Tiny gold nanoparticles can detect trace amounts of viruses by how their plasmon resonance shifts when molecules attach. The stained glass windows of medieval cathedrals, some owe their vibrant hues to similar nanoparticle effects, though none achieved the Lycurgus Cup's dynamic shift. That's what makes this artifact so extraordinary. It's not just an early example of nanotechnology. It's a masterpiece that still rivals what we can do today, born from flames and patience rather than electron microscopes. The cup's creators didn't know why their method worked, only that it did. They couldn't explain surface plasmons or wavelengths, but their hands understood the recipe. That's the true wonder here, science hidden inside art, waiting centuries for us to decode its secrets. Every time the glass shifts from green to red, it's not just a trick of the light. It's a conversation between past and present, where ancient craftsmanship nods to discoveries yet to come. If you think modern science could easily recreate the Lycurgus Cup's magic with all our cutting-edge tools, think again. In 2004, a team of researchers at the University of Cambridge set out to replicate the cup's exact properties, and what they discovered was humbling. Even with electron microscopes, spectrometers, and precisely calibrated furnaces, matching the Romans' craftsmanship proved maddeningly difficult. Their first attempts produced glass that either didn't change color at all or shifted in dull, uneven patches. The problem, getting those gold and silver nanoparticles just right. Too large and the effect vanished, too small and the glass turned murky. It took them over 50 trials to even come close. Here's the kicker, the Romans didn't have particle size analyzers or temperature-controlled kilns. They relied on intuition, honed through generations of glassmaking. Modern labs use chemical reactions to reduce gold and silver into nanoparticles, a process requiring exact pH levels and stabilizing agents to prevent clumping. The Romans likely ground the metals by hand, mixing them into molten glass at temperatures they judged by eye, yet their results were more consistent than many contemporary attempts. That's not just skill, it's borderline alchemy. Other teams have since cracked the code, but only by reverse engineering the cup down to the atomic level. In 2018, scientists at the Corning Museum of Glass used advanced spectroscopy to map the nanoparticles' distribution, revealing another layer of sophistication. The particles weren't just uniformly sized, they were spaced at optimal intervals to maximize the color shift. This spacing wasn't random, it followed a pattern that modern engineers would need computer simulations to replicate. The Romans, of course, had no such tools. They achieved this spacing through meticulous stirring and cooling techniques, a dance of heat and timing lost to history. What's even more telling is the energy required. Modern nanoparticle production often involves toxic chemicals or energy-intensive processes. The Romans did it with nothing but fire, crushed metal, and patience. Their method was sustainable in a way our labs are still struggling to match. When researchers at MIT finally succeeded in creating a Lycurgus-like glass in 2021, their report included an unexpected admission. The ancient technique might actually be more efficient for certain applications, bypassing the need for complex chemistry. These replication efforts don't just highlight how advanced Roman craftsmanship was, they expose a gap in how we view technological progress. We assume newer means better, but the Lycurgus Cup reminds us that innovation isn't always linear. Sometimes the past holds secrets we haven't yet rediscovered. Every failed modern attempt is a tribute to those unnamed artisans who 17 centuries ago turned sand, metal, and flame into something that still defies our best efforts. The cup isn't just a relic, it's a challenge, one that whispers across time, daring us to catch up. The Lycurgus Cup stands alone in the world of ancient glass, but it's not the only piece to play with light. Across the Mediterranean, other cultures experimented with dichroic effects, creating vessels that shimmered and shifted under changing angles. Take Byzantine glassware, for example. Skilled artisans crafted bowls and goblets layered with stripes of colored glass, alternating gold-infused yellows with cobalt blues. When tilted, these pieces seem to flicker between hues, catching the eye like sunlight on water. Beautiful, undoubtedly, but scientifically they're light, years behind the Lycurgus Cup's sophistication. The Byzantine approach relied on thick, visible bands of different glass types fused together. Light interacts with these layers macroscopically, bouncing off surfaces rather than being transformed at the molecular level. There's no nanoengineering here, just clever craftsmanship with materials already at hand. Then there's the famed Barberini Cup, another Roman masterpiece often mentioned in the same breath as the Lycurgus Cup. At first glance, they seem like siblings, both change color, both depict mythological scenes, both demand admiration. But peer closer, and the differences are stark. The Barberini Cup's color shift comes from sandwiched layers of glass-opaque white pressed against translucent red. When light hits from the front, the white dominates. When backlit, the red glows through. It's a stunning effect, but one achieved through basic optical principles any stained glass artist could explain. The Lycurgus Cup, by contrast, doesn't rely on layers at all. Its entire volume is uniform, with nanoparticles distributed evenly like stars in a galaxy. Where the Barberini Cup is a sandwich, the Lycurgus Cup is a soup, homogeneous yet somehow alive with hidden complexity. Even more telling are the scattered fragments of dichroic glass found in Egyptian and Syrian workshops. These shards occasionally show faint color changes, often due to impurities like copper or manganese oxidizing unevenly over centuries. But none exhibit the Lycurgus Cup's precise, instantaneous shift from green to red. Without controlled nanoparticle distribution, these pieces are accidents of chemistry, not deliberate feats of engineering. One Syrian beaker from the 5th century, for instance, turns a muddy purple when backlit, a far cry from the cup's vivid, theatrical transformation. What sets the Lycurgus Cup apart isn't just what it does, but how it does it. Every other ancient dichroic artifact manipulates light through bulk properties, thick layers, chemical gradients, or simple metal oxides. The cup alone operates on the scale of individual photons, harnessing quantum effects no one would understand for another millennium. It's the difference between painting with a brush and painting with a single atom. That's why, even among its peers, the Lycurgus Cup feels like an outlier, a relic that somehow slipped through time, carrying secrets the rest of its era could barely glimpse. The Romans had no concept of nanotechnology, no electron microscopes to see the particles they were manipulating, yet somehow they infused glass with gold and silver so finely ground, the results still dazzle scientists today. How did they achieve such precision? The truth is, we may never fully know. When the Western Roman Empire collapsed in the 5th century, entire schools of craftsmanship vanished overnight. Glassmaking wasn't just a trade, it was an oral tradition passed down through generations in workshops where secrets were guarded like treasure. The Lycurgus Cup might be the lone survivor of techniques lost to history, techniques so advanced we're still piecing together how they work. One theory points to colloidal gold, a suspension of ultra-fine gold particles in liquid. Historians speculate Roman artisans could have created this by dissolving gold in aqua regia, a potent mix of nitric and hydrochloric acids known since antiquity. They'd then reduce the solution, leaving behind nanoparticles suspended in liquid. Stirred into molten glass, this colloidal gold would distribute evenly, creating the uniform particle sizes we see in the cup. The catch: no surviving texts describe this process, and the acid mixtures involved were volatile. A single misstep could mean wasted gold or worse, explosions. Yet the evidence is in the glass itself. Those 50-nanometer gold flecks didn't appear by accident. Another possibility involves annealing, the slow cooling of glass to relieve internal stresses. Roman furnaces were capable of precise temperature control, as seen in their intricate millefiori glassware. For the Lycurgus Cup, artisans might have used a multi-stage annealing process, cooling the glass at specific rates to prevent nanoparticles from clumping. Too fast and the metal particles would bunch together; too slow and they might grow too large. Modern experiments show that annealing at around 600 degrees Celsius yields similar nanoparticle distributions, but without written records, we're left guessing how Romans calibrated their kilns. Did they use temperature-sensitive clays as indicators? Observe color changes in the molten glass. The answers died with them. Perhaps the most intriguing theory revolves around glassmaker's soap, a term medieval artisans used for manganese dioxide, added to glass to remove unwanted tints. Some researchers suggest Romans could have used similar additives to stabilize gold and silver during melting. A pinch of tin or lead, for instance, might act as a surfactant, keeping nanoparticles separated. This would explain the cup's flawless particle spacing, but again, no recipe survives. The greatest loss wasn't just the methods, but the mindset. Roman glassmakers didn't see themselves as scientists. They were craftsmen pushing materials to their limits through intuition and observation. Their failures likely outnumbered their triumphs, with countless experiments ending in shattered glass or murky colors. The Lycurgus Cup is the exception, the one masterpiece that survived the chaos of falling empires, reminding us how much knowledge can slip through the cracks of time. What's haunting isn't just what we've lost, but what it implies. If they could engineer nanoparticles without understanding atoms, what other breakthroughs vanished when Rome fell? The cup is a whisper from a world that might have leapfrogged centuries of scientific stagnation, if only its secrets hadn't turned to dust. Why would a cup this extraordinary exist just to hold wine? The Lycurgus Cup's staggering craftsmanship suggests it was far more than a drinking vessel. It was likely a ceremonial object, designed to astonish and evoke deeper meaning. One compelling theory ties its color shift to the rituals of Dionysus, the god of wine and ecstasy depicted in its carved scene. Imagine this cup passing hands at an imperial feast, filled to the brim with dark red wine. Under torchlight, the glass would glow green, its surface alive with Lycurgus's struggle. But as the drinker raised it to their lips, backlit by flickering flames, the green would dissolve into a translucent crimson, mirroring the wine's own hue. The effect would be uncanny, as if the myth itself unfolded in real time. Vines tightening around the king, the god's wrath manifesting in the vessel's metamorphosis. This wasn't just theater, it was theology in glass. In Dionysian rites, wine symbolized both life and blood, a duality the cup's shifting colors could physically embody. Green for the vitality of grapes, red for the sacrifice required to transform them. Some scholars argue the cup might have been used in private initiations, where its optical illusion served as a metaphor for spiritual transformation, a tangible representation of the mysteries participants were meant to internalize. Others see a darker political message. The Roman elite adored displays of power that blurred the line between the divine and the mortal. An emperor sipping from this cup wouldn't just be drinking, they'd be performing. The color shift could symbolize their authority over nature itself, their ability to command even light to bend to their will. There's precedent for this. Nero famously dined beneath ceilings that rained perfume, while Domitian hosted banquets in rooms paved with moonstone to mimic night. The Lycurgus Cup fits this tradition, a flex of imperial ingenuity, proving Rome's mastery extended beyond armies and into the realm of the unseen. Yet the most intriguing possibility is that the cup served multiple roles. Ritual object one moment, status symbol the next. Its dichroism wasn't just decorative, it was interactive, changing based on how and where it was held. This adaptability would have made it endlessly fascinating, a conversation piece that invited awe each time it passed between hands. Whether used in temple ceremonies or palace feasts, its magic wasn't just in the glass, but in the way it transformed ordinary moments into encounters with the extraordinary. What's striking is how few objects from antiquity command this level of engagement. Most ceremonial artifacts are static, their meaning fixed. The Lycurgus Cup demands participation, its full brilliance revealed only through interaction. That intentionality speaks volumes. This wasn't just a cup meant to be seen. It was one meant to be experienced, a bridge between worlds crafted in glass and gold. And in that space between ritual and revelation, it remains as enigmatic today as it was 17 centuries ago. The Lycurgus Cup may be the most stunning example of ancient nanotechnology, but it's not the only artifact that hints at lost scientific brilliance. Take Maya blue, the vibrant pigment that still clings to murals and pottery centuries after other colors have faded. Unlike traditional dyes, this turquoise hue wasn't derived from simple minerals. It was a complex blend of indigo and palygorskite clay, heated to just the right temperature to bond at a molecular level. The result, a pigment so resistant to time and weather that it outlasts the temples it adorns. Modern analysis reveals the Maya-engineered nanostructures within the clay, creating a crystalline framework that locked the indigo in place. While not as precise as the Lycurgus Cup's gold particles, it's another case of ancient artisans manipulating matter invisibly small. Then there's Damascus steel, the legendary blades that could slice through armor without dulling. Forged between the 3rd and 17th centuries, these swords weren't just strong, they were flexible, with a distinctive wavy pattern dancing along their surface. The secret lay in their composition. Raw iron from India, known as woot steel, contained trace amounts of vanadium and other rare elements. When smelted under precise conditions, these impurities formed carbon nanotubes within the metal, reinforcing it at the microscopic level. Unlike the cup, this wasn't an optical trick but a feat of material science, one that vanished when the woot supply dried up. Centuries later, metallurgists still debate how blacksmiths achieved such consistency without modern tools. Even older is the zinc-rich brass from 1st century Palestine, found in coins and decorative objects. Recent studies show these alloys contain nanowires, threads of metal, just atoms thick, likely formed during an advanced smelting process. Like the Romans, these craftsmen couldn't see what they were creating, but they recognized the superior properties of the end product. What sets the Lycurgus Cup apart, though, is its intentionality. While Maya blue and Damascus steel showcase accidental nanotechnology, happy byproducts of empirical methods, the cup's design demanded precision. Its color shift wasn't a side effect, it was the entire purpose. Other ancient objects may whisper of nanoscale manipulation, but the cup declares it, proving that at least some artisans didn't just stumble upon these techniques, they mastered them. These scattered examples form a mosaic of forgotten knowledge, each piece revealing how much we've underestimated the past. Whether through pigment, steel, or glass, our ancestors were playing with forces they couldn't name but learned to harness. The Lycurgus Cup doesn't just stand alone, it invites us to wonder what other secrets still lie buried, waiting for the right tool, the right eye, to bring them back into the light. By the time medieval artisans set to work on stained glass windows for Europe's grand cathedrals, the secret of the Lycurgus Cup had long been forgotten. The vibrant blues and reds of Chartres or Notre Dame are breathtaking, but they rely on crude methods compared to Rome's nano-engineered marvel. Medieval glassmakers achieved their colors by adding metal oxides to molten glass, cobalt for blue, copper for red, manganese for purple. The results were stunning but static. Unlike the Lycurgus Cup's dynamic shift, these hues stayed locked in place no matter how the light changed. The difference lies in scale. Where Roman craftsmen manipulated particles invisible to the eye, medieval workshops worked in bulk, dissolving metals into glass by the handful. Their red glass, for instance, owed its color to colloidal gold, but the particles were far larger and unevenly distributed, creating a rich, uniform tint rather than a responsive color shift. Even the most skilled Gothic artisans couldn't replicate the Lycurgus effect because they lacked the precise control over particle size and spacing that defined Roman nanotechnology. Their glass was beautiful, but it didn't play with light, it simply absorbed or reflected it. Renaissance glassmakers fared no better. Venetian craftsmen on Murano perfected cristallo, a crystal-clear glass so flawless it rivaled rock crystal. They experimented with gold and silver, too, creating delicate pink and amber hues. Yet none of their surviving works exhibit dichroism. The closest they came was aventurine glass, where copper crystals scattered light in a glittering effect, but this was a happy accident, not engineered precision. When Renaissance scholars rediscovered ancient texts describing the Lycurgus Cup's properties, they dismissed them as myths. To them, the idea of color-changing glass was as fantastical as alchemy turning lead into gold. What's telling is the technological regression. Medieval and Renaissance glassmaking advanced in other areas. Stained glass windows grew larger, forms more intricate, colors more varied. But the ability to manipulate light at the nanoparticle level, that vanished with Rome. Even the famed Byzantine glassmakers, inheritors of Roman traditions, never replicated the cup's magic. Their dichroic pieces relied on layered glass, not embedded nanoparticles. It's as if the knowledge hit a dead end, leaving later artisans to reinvent the wheel without realizing what had been lost. This gap underscores a sobering truth. Technological peaks aren't always sustained. The Romans reached heights in material science that wouldn't be matched until the modern era, then saw those skills crumble with their empire. The Lycurgus Cup isn't just a relic of ancient genius, it's a measuring stick showing how far glassmaking fell before it climbed again. Every medieval stained glass masterpiece, every Renaissance goblet is a testament to human creativity. But none whisper across the centuries with quite the same defiance as that little cup, still glowing green and red like a beacon from a forgotten future. For centuries, the Lycurgus Cup sat quietly in museum collections, its secrets hidden behind glass thicker than the nanoparticles inside it. Then came the mid-20th century, a golden age of physics where scientists began probing how light interacts with matter at scales previously unimaginable. Researchers studying electron behavior in metals stumbled upon a peculiar phenomenon. When light struck nano-sized metal particles, it didn't just bounce off, it danced. The electrons on the particle's surfaces would oscillate in waves, absorbing and scattering specific colors of light with extraordinary precision. They called this surface plasmon resonance, and it would revolutionize fields from medicine to telecommunications. But here's the twist. While these scientists celebrated their discovery as groundbreaking, they'd unknowingly rediscovered what Roman artisans had harnessed 1700 years earlier. The Lycurgus Cup became an unlikely muse for modern plasmonics. When researchers finally analyzed its glass under electron microscopes in the 1960s, the shock was palpable. Those golden flecks suspended in the cup weren't just decorative, they were perfect plasmonic nanostructures, engineered to manipulate light with a finesse that matched cutting-edge lab creations. Suddenly, an artifact dismissed as a curiosity became a Rosetta Stone for nanotechnology. The implications were staggering. Modern scientists realized that by tweaking the size and spacing of metal nanoparticles, just as the Romans had, they could design materials with unprecedented control over light. Today, this principle powers everything from hypersensitive medical tests to ultra-efficient solar panels. Cancer diagnostics use gold nanoparticles to detect trace biomarkers, their plasmonic shift signaling disease earlier than conventional methods. High-tech windows tint dynamically by embedding nanoparticle layers, mimicking the cup's color change on demand. Even the vivid hues of some stained glass restorations owe their brilliance to rediscovered Roman-era techniques. What's poetic is how history folded back on itself. The same phenomenon that made the Lycurgus Cup a ceremonial wonder now drives quantum computing research. Those nanoparticles that once symbolized Dionysus's wrath today help engineers design optical circuits faster than silicon. The cup didn't just inspire modern plasmonics, it humbled it. Here was proof that nanotechnology wasn't solely the domain of futuristic labs, but a craft mastered by hands that worked by firelight. Perhaps most remarkable is how the past informed the future. When 21st century scientists sought eco-friendly ways to produce nanoparticles, some turned to ancient methods, grinding metals with mortars, using plant extracts as stabilizers, echoing techniques Romans might have recognized. The Lycurgus Cup stopped being a relic and became a mentor, its silent lessons whispering across millennia. In labs worldwide, researchers now speak of it not as a curiosity, but as the first known plasmonic device, a bridge between the empirical genius of antiquity and the algorithmic precision of modernity. The science hidden within the Lycurgus Cup isn't just a historical curiosity, it's the foundation of technologies shaping our world today. Take medical diagnostics, for instance. Modern rapid tests for diseases like malaria or COVID-19 use gold nanoparticles to detect trace amounts of viruses or antibodies. Just as the cup's gold flecks scatter specific wavelengths of light, these nanoparticles are engineered to bind to target molecules, creating visible color changes that signal infection. The principle is identical: metal nanoparticles interacting with light at scales invisible to the eye. But where the Romans crafted beauty, today's scientists save lives. The same plasmonic effects that made the cup shimmer now enable handheld devices to diagnose illnesses in minutes, even in remote villages without labs. Stained glass has also come full circle. While medieval artisans lost the Romans' nano-precision, modern conservators are reviving these ancient techniques to restore centuries-old windows. By embedding nanoparticles into glass, they can recreate the exact hues of original medieval panels without the fading or discoloration that plagued earlier methods. Some artists even push further, designing dynamic glass installations that shift color like the Lycurgus Cup, architectural marvels that transform buildings into ever-changing canvases of light. The difference: today's creators understand the physics behind the magic, allowing them to manipulate effects with laser precision. Perhaps the most unexpected application lies beyond our atmosphere. Spacecraft venturing into deep space face deadly cosmic radiation, and traditional shielding adds unsustainable weight. Engineers now experiment with ultra-thin films infused with gold nanoparticles, mimicking the Lycurgus Cup structure. These films scatter harmful radiation while remaining feather-light, a solution that could protect astronauts on missions to Mars. It's a poetic twist. Technology inspired by a Roman drinking vessel might one day enable interplanetary travel. Even everyday items harness these principles. self-tinting sunglasses, conductive inks for flexible electronics, and even some sunscreen formulations rely on nanoparticle interactions discovered through studying artifacts like the cup. What began as an artistic experiment in a 4th century workshop now permeates industries the original creators couldn't have imagined. The true legacy of the Lycurgus Cup isn't just in museums, it's in the invisible architecture of our modern world, where ancient ingenuity meets cutting-edge innovation. Those minuscule flecks of gold and silver, once thought to be decorative flourishes, turned out to be blueprints for a scientific revolution, and the most astonishing part. We're still uncovering new ways to apply what the Romans glimpsed 17 centuries ago. Their masterpiece wasn't just ahead of its time, it was a message in a bottle floating across millennia to guide the future. Every groundbreaking artifact seems to attract its share of conspiracy theories, and the Lycurgus Cup is no exception. Some fringe theorists insist its advanced nanotechnology couldn't possibly be the work of human hands, pointing to its color-shifting properties as evidence of extraterrestrial intervention. They argue that 4th century artisans lacked the knowledge to manipulate matter at such a microscopic scale, suggesting the cup was either a gift from alien visitors or crafted using forgotten technology from a lost civilization. But here's the problem with that logic. It underestimates the ingenuity of ancient cultures. We've already seen how Roman glassmakers achieved similar effects through meticulous trial and error, grinding metals to dust and observing how they interacted with light. The cup's craftsmanship, while extraordinary, aligns with known Roman techniques just pushed to their absolute limits. Another popular claim ties the cup to secret societies, alleging it was created by a shadowy group with access to forbidden knowledge. Proponents of this theory often reference the Dionysian themes in the cup's design, suggesting it was used in clandestine rituals to communicate hidden truths. While it's true the cup likely held ceremonial significance, its mythic imagery and optical illusions would have made it a powerful symbol in religious or political contexts. There's zero historical evidence linking it to any organized secret order. Roman elites were certainly fond of ostentatious displays of power, but attributing the cup to a clandestine cabal ignores the simpler explanation. It was a masterpiece commissioned by someone wealthy enough to afford the best artisans of the era. The most persistent myth, though, is the idea that the cup's technology was deliberately suppressed by later civilizations. Some speculate that medieval churches destroyed knowledge of nanoparticle engineering to maintain control over stained glass production, while others claim the technique was stolen and hidden by rival empires. But the truth is far less dramatic. Technological regression happens throughout history. Skills fade when societies collapse, trade routes shift, or materials become scarce. The fall of Rome disrupted countless crafts, from concrete making to hydraulic engineering. The loss of nanoparticle glassmaking wasn't a conspiracy. It was a casualty of time and chaos, like so many other ancient innovations. What's fascinating is how these theories reveal more about us than the cup itself. We're quick to assume that unexplained brilliance must stem from something otherworldly or clandestine, rather than acknowledging the sheer creativity of human minds. The Lycurgus Cup doesn't need aliens or secret societies to be awe-inspiring. Its real story of artisans pushing boundaries without microscopes or textbooks is miraculous enough. The next time you hear a wild claim about this ancient marvel, remember, sometimes the most extraordinary truths are the ones rooted in ordinary human genius. Walk through the doors of the British Museum's climate-controlled treasure vaults, and you'll find the Lycurgus Cup resting in a specially designed case that's more high-tech than most modern laboratories. This isn't just display glass protecting it. This is a micro-environment engineered to mimic the exact conditions that have preserved the cup for 17 centuries. Temperature and humidity sensors maintain a constant 20 degrees Celsius with 50% relative humidity, shielding the delicate glass from thermal shock or moisture damage. Even the air inside the case is filtered to remove pollutants that could degrade its surface over time. The cup may have survived the fall of Rome, but today's curators aren't taking any chances. Light exposure is another battlefield. Unlike ordinary artifacts that can tolerate gallery spotlights, the Lycurgus Cup's nanoparticles make it uniquely vulnerable. Prolonged light, especially ultraviolet wavelengths, can cause irreversible fading or structural stress. To combat this, the museum employs LED lighting calibrated to emit only the safest wavelengths, and even then for strictly limited durations. The cup spends significant time in darkness, emerging only for carefully scheduled viewings or research. Ironically, an object that plays with light so brilliantly must now hide from it to survive. But preservation isn't just about defense, it's about preparation. In 2019, the museum launched a groundbreaking 3D scanning project to map the cup's structure down to the micron level. Using structured light scanners, researchers created a digital twin so precise it reveals tool marks invisible to the naked eye, including evidence of how Roman artisans polished the glass. This isn't just archival diligence, it's a contingency plan. Should disaster strike, these scans could guide restoration or even replication. The data also lets scientists study the cup's nanoparticles non-invasively, revealing distribution patterns that hint at lost crafting techniques. Every scan peels back another layer of mystery, proving that even in stillness the cup continues to teach. Perhaps most surprising is what the museum doesn't do: restore. Unlike paintings or bronzes, the cup shows no corrosion or pigment loss, so conservators adhere to a strict do-no-harm philosophy. No cleaners touch its surface, no adhesives repair hypothetical flaws. This restraint acknowledges a profound truth: the cup's resilience lies in its original craftsmanship. Those Roman nanoparticles haven't degraded because they were engineered to last. Modern interventions could disrupt delicate equilibrium science doesn't fully understand. The real triumph of these efforts is how they balance access with preservation. The cup isn't locked away entirely, it's shared strategically. Its display case positioned to allow visitors to witness its color shift without compromising its safety. School groups lean in as docents demonstrate the lighting trick, their gasps echoing those of banqueters 1500 years prior. In this way, the museum honors both the artifact's physical needs and its role as a bridge across time. The Lycurgus Cup survived empires, but its future now depends on something equally fragile: our willingness to protect wonder. Modern technology is peeling back layers of the Lycurgus Cup's secrets in ways its creators could never have imagined. Recent advancements in CT scanning and spectral imaging have transformed this ancient artifact into a digital playground for researchers, revealing hidden intricacies that even the most meticulous examination under glass could never uncover. When scientists at the British Museum subjected the cup to high-resolution CT scans, they discovered something astonishing: the glass isn't uniformly thick. Subtle variations in thickness, some areas barely a hair's breadth thinner than others, were deliberately crafted to enhance the play of light through the nanoparticles. These minute adjustments act like a natural amplifier, intensifying the color shift in specific areas where the myth's drama unfolds most vividly. It's as if the artisans weren't just shaping glass, they were composing with light itself, tuning their material like a musical instrument. Spectral imaging took the investigation even deeper. By analyzing how the cup reflects and absorbs different wavelengths of light, researchers mapped the exact distribution of gold and silver nanoparticles in 3 dimensions. The results upended previous assumptions. Instead of being randomly scattered, the particles cluster slightly denser around the figures of Lycurgus and the vines. A discovery that suggests the color shift wasn't just a neat trick but a narrative device. When backlit, these denser concentrations make the king and his tormentors glow more intensely, as if the myth itself is being illuminated from within. This wasn't just craftsmanship, it was storytelling at the molecular level. perhaps the most surprising revelation came from micro-CT scans, which exposed tool marks invisible to the naked eye. The cup's interior surface, long assumed to be smooth, bears faint striations from the lathe used to polish it. These grooves, thinner than a human hair, follow a precise spiral pattern that would have required the artisan to adjust speed and pressure with extraordinary control. Even more telling, the grooves align perfectly with the nanoparticles distribution, suggesting the polishing process itself may have influenced how the metal flecks settled in the glass. What initially seemed like separate steps, shaping, embedding particles, polishing, now appear as parts of an integrated technique, each phase meticulously orchestrated to achieve the final effect. These digital reconstructions also settled a long-standing debate about the cup's missing pieces. For years, scholars speculated whether the foot and stem now attached to it were original or later additions. Spectral analysis of the glass composition confirmed the base is indeed a medieval replacement made from glass with entirely different trace elements. But the scans also revealed something poetic. The original stem likely broke along a stress point created by the nanoparticles distribution, hinting that the very feature that made the cup extraordinary also made it fragile. Every pixel of these scans tells a story not just of how the cup was made, but of the minds behind it. The artisans didn't have computers, but their understanding of materials was so profound, they achieved effects we're only now learning to measure. As these digital studies continue, they're doing more than preserving history. They're bridging a conversation across centuries where modern science and ancient ingenuity speak the same language. And with each new scan, the Lycurgus Cup reveals another layer of its genius, proving that some secrets aren't meant to stay hidden forever. The Lycurgus Cup's home in the British Museum hasn't gone unchallenged. Over the past decade, Italian cultural officials have quietly intensified efforts to repatriate the artifact, arguing it was almost certainly looted during the chaotic centuries following Rome's collapse. Their case hinges on historical records describing similar dichroic glassware found near Naples, suggesting the cup originated in workshops now lying within modern Italy. But the museum counters with a different perspective that as one of the few surviving examples of Roman nanotechnology, it belongs to the world, not just one nation. This debate taps into broader tensions swirling around colonial-era acquisitions, where the line between preservation and appropriation blurs. Complicating matters is the cup's fragility. Unlike marble statues or bronze relics, glass this ancient requires microclimate controls most regional Italian museums lack. When Greece successfully reclaimed the Parthenon marbles in 2023, critics noted cracks developing within months due to inferior humidity management. Proponents of keeping the cup in London argue its scientific and artistic significance demands the cutting-edge conservation only institutions like the British Museum can provide. Yet others question whether such reasoning perpetuates a paternalistic dynamic, where former colonial powers position themselves as sole guardians of global heritage. Meanwhile, a separate ethical dilemma simmers in laboratories. As 3D printing and nanotechnology converge, researchers now possess the tools to create near-perfect replicas of the cup particle distribution and all. In 2021, a Swiss team successfully printed a functional copy using gold nanoparticle-infused resin, sparking debates about authenticity versus accessibility. Should museums display replicas while safeguarding originals in vaults? Could 3D scans allow the cup to be repatriated digitally, sharing its secrets without physical transfer? Purists shudder at the idea, insisting no copy can capture the aura of an object touched by 4th-century hands. But for schoolchildren in rural Italy who may never visit London, a meticulously crafted duplicate might be the closest they'll get to their cultural inheritance. Beneath these arguments lies a deeper philosophical rift. The cup exists at the intersection of art, science, and identity. Is its primary value as a research specimen, a masterpiece, or a national symbol? Modern technology could theoretically produce thousands of copies, diluting its uniqueness yet democratizing access. But would that diminish the original's power or amplify its legacy? The Romans who crafted it likely never imagined their work would spark such questions 1700 years later. Their creation now serves as a mirror, reflecting how we balance preservation with justice, innovation with tradition, and ownership with shared human heritage. In that sense, the cup's true dichroism isn't just in its glass, it's in the way it reveals different truths depending on who holds it and in what light. The secrets of the Lycurgus Cup are far from fully unlocked. Scientists are now preparing to probe deeper than ever before, armed with tools that would seem like magic to its original creators. One groundbreaking study on the horizon involves nanoscale particle mapping using synchrotron radiation, a technique that fires intense X-ray beams to trace the three-dimensional arrangement of every single gold and silver fleck within the glass. This isn't just about cataloging nanoparticles. Researchers hope to reconstruct the entire fabrication process by analyzing how particles cluster around tool marks and thickness variations. Think of it as forensic archaeology at the atomic scale, where each particle's position might reveal whether the glass was stirred clockwise or how long it cooled before annealing. Meanwhile, experimental archaeologists are taking a radically hands-on approach by reconstructing Roman furnaces down to the last brick. At Bradford University, a team spent 2 years studying kiln remains from Pompeii to build a working replica capable of reaching Roman glassworking temperatures. Their goal, to test whether nanoparticle effects could be achieved through documented ancient methods grinding metals with stone mortars, mixing them with plant ash as flux, and judging melt consistency by eye. Early trials have yielded intriguing results, with some batches showing faint dichroic effects when gold is ground for over 12 hours. The process is painstaking, requiring artisans to work in period-accurate conditions, no thermometers, no protective goggles, just firelight and experience passed down through generations of craft. What makes these studies revolutionary is their potential to bridge the gap between ancient knowledge and modern understanding. By combining space-age analytical tools with Stone-Age techniques, researchers might finally solve how Roman artisans achieved such precise control without microscopes or precision scales. Some theorize they used natural phenomena like the Tyndall effect, where sunlight passing through colloidal solutions reveals suspended particles, as primitive quality control. Others suggest secret additives like urine or vinegar could have stabilized nanoparticles during melting. Each new experiment peels back another layer of this ancient technological mystery. Perhaps most exciting is how these investigations could rewrite the history of innovation. If Roman furnaces can reliably produce nanoparticle effects, it would suggest their discovery wasn't accidental but systematic, the product of generations of observation and refinement. We might be looking at the remnants of an entire school of materials science, lost when Rome fell and only now being resurrected through flame and patience. As these studies unfold, they promise more than just answers about one cup. They could reveal how much ancient civilizations truly understood about the invisible world around them. Every fresh discovery in this field doesn't just illuminate the past, it challenges our assumptions about what's possible when human curiosity meets relentless experimentation. The Lycurgus Cup isn't just an artifact, it's a revolution disguised as a drinking vessel. Think about it, 17 centuries ago, Roman artisans manipulated matter at a scale so small, it wouldn't even be visible again until the invention of electron microscopes. They ground gold and silver into particles finer than pollen, suspended them in glass with near-perfect uniformity, and engineered a material that plays with light like a cosmic chameleon. This wasn't accidental alchemy, it was precision nanoengineering achieved without a single textbook or lab coat. The cup's very existence forces us to rewrite the history of science. We've long assumed technological progress marches in a straight line, each era building on the last, but the Lycurgus Cup shatters that myth. It's proof that brilliance can bloom in unexpected places, then vanish for centuries, leaving future generations to rediscover what was once known. What's even more humbling is how much this cup redefines our understanding of ancient innovation. For years, historians framed the Romans as master builders and conquerors, not materials scientists. Yet here's an object that rivals modern plasmonic devices, crafted in an era when atoms were just philosophical speculation. The cup doesn't just belong in a museum, it belongs in engineering textbooks, right alongside quantum dots and nanotube arrays. Its nanoparticles don't just scatter light, they scatter our assumptions about what ancient civilizations were capable of. If they could achieve this without microscopes or particle accelerators, what else did they know that we've since forgotten? And that's the real question looming over this tiny chalice. The Lycurgus Cup can't be alone. Somewhere in the dust of history, there must be other artifacts whispering of lost technologies, objects that, like this cup, were dismissed as curiosities until new tools revealed their secrets. Maybe it's a Babylonian lens with unexpected optical properties, or an Incan alloy with inexplicable durability. Perhaps there are entire schools of ancient science waiting to be rediscovered, their techniques buried in plain sight. The cup is a reminder that history isn't a puzzle we've nearly solved. It's a labyrinth with hidden corridors we've yet to explore. So the next time you hear about some ancient artifact with inexplicable properties, don't dismiss it as a fluke or a hoax. Remember the Lycurgus Cup glowing quietly in its museum case, defying expectations with every color shift. It's not just a relic of the past, it's a beacon for the future, urging us to look closer, dig deeper, and stay humble in the face of human ingenuity. After all, if 4th century glassmakers could bend light to their will with nothing but fire and patience, what other miracles might still be waiting unnoticed in the shadows of history?